In our previous videos, we have talked about this equation y prime prime plus y equals 0. This is what we call a homogeneous linear differential equation of order 2, and we have found its most general solution, which is a constant times sine x plus another constant times cos x. Well, now let's generalize the right hand side and solve for a differential equation y prime prime plus y equals a function of x. This is what we call a non-homogeneous equation, as opposed to the previous one, which is called a homogeneous equation. And firstly, before we talk about some specific cases of fx where it is easy to solve, well, I would first introduce you can say theorem or an explanation of what we will do in the following cases. So the claim is, if y naught, so a particular function y naught, is a solution, so not all the solution but just a single solution, for y prime prime plus y equals fx, then the general solution for the same equation is y equals y naught plus the answer for the homogeneous case, which is a sine x plus b cos x. So what this claim or theorem tells us is that we just have to find one single solution for that equation, and the general solution would be just that particular solution add the solution for the homogeneous case. And the proof is easy. Because since y naught prime prime plus y naught equals fx, if there were another solution, then we can subtract both equations to get y minus y naught prime prime plus y minus y naught equals 0, because in both cases the right hand side is fx, we subtract, they cancel out. But the general solution for this is a sine x plus b cos x, and hence if there were any other solution, it must be in the form y naught plus a sine x plus b cos x. So the moral of the story is we just have to find one particular answer, and that will be called a particular integral. Well, at least that's the technical name for it. So let's look at some simple examples and then move on to the really hard ones. So let's say y prime prime plus y equals, say, sine 3x. Well, what we can do, because what we want to do is to find one single solution, we can test whether a certain family of functions will satisfy this. So let's say we just test y as a function of x. Let's say a sine x 3x plus b cos x 3x, and see whether for some suitable a and b this function would satisfy that equation. So y prime would be 3a sine, 3a cos 3x minus 3b sine 3x. Y prime prime would be 9a, well, negative 9a sine 3x minus 9b cos 3x. So if these two sum, y plus y prime, were to be equal to sine 3x, it must be equal to this. And we can obviously see a particular pair of AB that obviously works. So 1/8 for A and 0 for B obviously works. The right hand side will be sine 3x. And what we're doing here is not something that is, well, there isn't a flaw in this logic, because what we're trying to do is to find one single solution. We're not trying to find all of them. So you might ask, oh, what if there are other possibilities for A and B? But that would be pointless, because we already found one that works. So y equals negative 1/8 sine 3x is a solution. And so we can, by the claim, conclude that the general solution is y equals 1/8 sine 3x plus a sine x plus b cos x. Well, so that's the simple example where we can use test functions. So if the right hand side were to be like a polynomial, you can also test with polynomials and see which polynomials satisfy it. And for those kind of simple functions, you can try to test some functions. But if fx were to be something complicated, for example, y prime prime plus y equals tangent x, and trust me, you will go nowhere by testing some functions. So because, well, with the benefit of hindsight, I know the answer to be very long and complicated. So well, testing wouldn't give you much. So we have to find a general procedure to solve the non-homogeneous case. And indeed there is one, well, albeit it's quite complicated, but it's a systematic way that we can do. So first of all, well, again, I have to remind all of us that we are trying to find one single solution, not all of the solutions yet. So let's look at the motivations of what we're going to do next. So the motivation is the solution for this equation, as we already know by now, is a sine x plus b cos x. What I'm going to do to hopefully find a solution to this, and trust me, it will work, is to let y be the same thing, but a and b would become functions instead. So a and b would become functions instead. And you will find functions a and b that satisfy this. So let's try to find y prime. Well, now that a and b are functions, we have to make use of the product rule. So it is not just a cos x minus b sine x. There is also the extra term of a prime. Well, I will not write the x anymore because it will be quite messy. So I can actually just, well, you just have to remember that a and b are also functions. Plus a prime sine x plus b prime cos x. Okay, but then if we move on to y prime prime, there would be 8 terms, and again it will be quite messy. So what I'm going to do here is to do a very bold move. I will assume a prime sine x plus b prime cos x to be 0. Well, it doesn't hurt, because what we want to find in the end is an example for a and b, and as you will see afterwards, we can still find a and b subject to this new condition. So if that thing were to be 0, then y prime prime would be just differentiating this part, which is negative a sine x minus b cos x. Well, again, we still have to use the product rule, so plus a prime cos x minus b prime sine x. And notice this is actually just minus y, and it makes sense because if we do the same thing with a and b constant, this would be the exact result that you would get upon substituting that function into this part. So what we now know is y prime prime plus y is a prime cos x minus b prime sine x. And we want this to be tangent x, because the equation we are solving is y prime prime plus y equals tangent x. So now we just ask ourselves, can we solve these two equations? And indeed, this is just kind of like a simultaneous equation with variables a prime and b prime. So yes, it is possible. And in fact, I will write it in a more neat notation, which is like this. So sine x, cos x, and negative sine x. This times a prime b prime equals 0 tangent x. And you can check for yourself, this matrix is actually the inverse of itself. It's actually the inverse of itself. It's easy to check that. And so you know a prime b prime is sine x cos x minus sine x times 0 tangent x. You can solve this, and this is sine x on the top and minus sine squared x over cos x at the bottom. Okay, so now we just want to find a particular example for a and b, so that's easy. A prime would be, well, a would be the integral of sine x dx. And we just want one particular integral. We don't have to add the c, the constant c. We just want to find one particular example for a, and of course that's minus cos x. And b would be the integral of, well, minus sine squared over cos x dx. I will write this as, well, sine squared x is 1 minus cos squared x. So this is actually cos x minus 1 over cos x, as you can verify. So this would be sine x minus the integral of the secant of x, which deserves another video, but I will tell you the answer for this. This is the natural log of the secant of x plus the tangent of x. Okay, this is quite complicated, but I will indeed write this in a, well, not to say neater form, but it will look nicer at least. So this is the same thing as this plus the ln of this, and you can verify that this is actually just secant of x minus tangent of x. You can utilize the fact that secant squared minus tangent squared is 1. Okay, now we just found examples of a and b. So we just plug it back in and we can find a particular solution. So y is a sine x plus b cos x. We know what a is. Let's look. A is minus cos x. And b is this very long expression times cos x. Well, we can look at some terms that cancel. So in the end, we get cos x times the natural log of secant x minus tangent x. So in conclusion, this is a solution to our original differential equation. And as I said, it's quite a complicated one, and therefore test functions won't really help much. But now, using this technique, which is to swap the constants into functions and also add this particular condition to simplify our workings, we can actually find a prime and b prime, and then hence a and b. So what's the general solution? The general solution to y prime prime plus y equals tangent x is y equals the cosine of x times natural log of secant x minus tangent x plus a sine x plus b cos x. Of course, this a and b are different from the a and b we had just now. This a and b is due to the fact that we have to add the solution to the homogeneous case. So in this case, a and b are constants. And this is the general solution. Of course, we can generalize this to a general fx, and I also invite you to write an expression for the general case y prime prime plus y equals fx, and use the same techniques. You can find a closed form. Of course, you have to use integrals to write the whole thing out, but indeed you can find a particular solution, or what they call a particular integral of this differential equation. And hence, after you find that, you just plug in, you just slap the final term of a sine x plus b cos x, and you're done. And yep, this is how you solve a non-homogeneous differential equation.